Alright, so on our agenda today, we're going to finish Chapter 13, start Chapter 14. We'll be in 14 for a long time, seemingly a long time. It goes pretty fast. You have Mastering due tonight, which is over Chapter 13, and then you have Mastering Wednesday, which is on Chapter 14. We'll do a group quiz on Friday, and I have your exam for you to take home at the end of class. Good. Alright. So the last thing we had in Chapter 13 was just what is a catalyst and then how does it affect reactions. So this slide is from like middle of the pack. Somehow, when I was designing this, it made sense to have it separate, but it really doesn't. It doesn't make any sense at all. So the question is, what is a catalyst and why do we care about it? So a catalyst is any substance added to a reaction that seemingly speeds up the reaction, but is not consumed by the reaction. So it's not an intermediate. A catalyst is a reactant. It's like halfway in the pack. In 13, yeah, it's like the last two things. This 18 slide. Yeah, slide 18-ish. Alright, so a catalyst is not an intermediate. It is not a product. It is something added to the beginning of a reaction. Alright, but it's not consumed. So, I have hydrogen peroxide, which if I let hydrogen peroxide just sit out in the air, eventually it'll become water and oxygen. But if I want this reaction to move along faster, I would add this manganese dioxide. The manganese dioxide appears as both a product and a reactant, because while it catalyzes the reaction, it is not part of the reaction. So when we think about what does it mean to catalyze the reaction, right, this reaction up here has a certain activation energy, shown by my graph. Is this an exothermic or endothermic reaction? It's an exothermic reaction, right? So if I was looking at exothermic, right, that is the activation energy. Now my new reaction has this manganese dioxide, this catalyst. It lowers the activation energy. So by using a catalyst, it seemingly is faster, but it's because it has less activation energy needed to get the product. So it's not changing how it does it, it's just making the activation energy lower. Right, we see catalysts all the time in biology, animal science, right? There's all kinds of catalysts in your system. So how does that apply to when we are thinking about kinetics and elementary steps? It can provide some new options for elementary steps. Let's say I have this reaction Alright, it's some elementary steps in a series of steps. We'll go ahead and make it easy and say it's a slow elementary step in my series of reactions. If it is the slow elementary step, then what do the exponents refer to in my rate law? The coefficients, right? So the rate equation for this reaction what is the overall order for this reaction? 3, right? It's a third order overall, because I have 2 plus 1. Well, if we added the manganese catalyst, there's a way that we can, so this is a third order. What has to happen for this reaction to go forward then, based on this? Physically, what has to happen to make a product? How many different molecules have to collide simultaneously to make this happen? 3. You have to have 3 molecules all collide together with the right amount of energy in the right orientation at the right speed to make a product. That is complicated, right? It's hard enough to get 2 things to slam into each other, but to try and get a third molecule to all slam in together all at the same time, all at the same speed, really, really hard. So, if we add a manganese catalyst, we can change the overall order of the reaction and make it speedier, more likely to happen. So, let's say alright, so by adding this manganese 2 plus catalyst, we'll have a new series of elementary steps. Alright, so now we have just one cesium reacting with the manganese. You would never be able to predict this. I would have to give all this information to him. Alright, so let's say we have this new series of elementary steps. If manganese 2 plus is the catalyst, I should have manganese 2 plus at the beginning of my reaction, and it should pop out the very last step at the end of my reaction. Is that the case? Yes, right? Here it is in the very first step going in, and manganese 2 plus is the very last thing coming out. So that's good. What are some things that will cancel out amongst these 3 reactions? This one, yeah, and one more, Mn4+. So the only manganese you see is the one you put in and the one that comes out. These other The ones in green are intermediate. And the ones in blue would be the catalyst. Right? Because the ones in green, product reactant, product reactant. They don't actually appear in the end. Alright, so then my net overall right, so it's the same reaction I had at the beginning. That's what I wanted. Last thing, if I wanted to write the rate law for this, which equation do I use? 1, 2, or 3? I use 1. Why do I use 1? It's the slow one, right? So we based on the elementary step that's the slowest. What exponents does the cesium and manganese have? They're both 1. Why can I have manganese 2+ in here? It is a catalyst, not an intermediate. If it was an intermediate, what would I have to do? I'd have to do some other stuff, right? I'd have to figure out some way to get, you can't have an intermediate in here, but because it's catalyst, totally fine. How many molecules have to collide now? Just 2. 2 have to find each other and slam into each other. That's a lower activation energy and more likely to happen. Yeah. Yep. It's, I put it in and I get it back out so I can measure its concentration. But these guys on the inside get used up as soon as they're made. There's no way for me to figure out how much of it there is. If that helps you think about it. You always know how much you put in, right? Because you weigh it out and you put it into the beaker. You can always figure out how much you have at the end, because you can weigh it out. The stuff on the inside, really hard to figure out how much you have, because it's being used up as fast as it's being made. So. Alright, my concluding thought on chapter 13. So, in general, we can measure reaction rates, little k's, either through initial rates, right, something like that, or graphically. Right, I can graphically do that, and then that's that, right, and then where that point is. So I can figure out reaction rates either one of those 2 ways. Once I've done, this is, right, that's the experimental part of it. Once you've done the experiment, you're going to postulate, or formulate a rate law. Right, whatever it is. And then based on your rate law, you can make some guesses as to what the elementary steps are that are involved. So, how do we use that to then talk about bigger reactions? And reactions that don't go to completion. So now we're ready to start talking about equilibrium. So up to this point, we've mostly just talked about reactions that have like one single direction arrow. Everything's going to products, which is good when we're talking about basic chemistry. But realistically, that doesn't happen. That's not actually how it works. In reality, all reactions can move in both directions. So for these kinds of reactions, we just had K, right? K tells us the rate constant. Right, and we would have, rate equals K. Alright, whatever that was. Well, that was baby steps. Only having it go in one direction. In reality, we could have a rate constant going forward. And we also have a rate constant going backwards. So K sub F for forward and K sub F for reverse. The reactions don't go only in one direction, so we need a rate constant for both directions. And then we want some way to quantify it. We want to figure out, is it more likely to go forward? Is it more likely to go backwards? Are we in the middle someplace? How much of each have I made? By the end of this chapter, you'll be able to do all that. Answer the big questions. Like on a chemistry scale. Like not really the big life questions, but like, is my reaction going to proceed? So, we are now ready to start talking about states of equilibrium. With this weekend just like crazy because you guys seem really low energy. Too much excitement, the Vegas night, the nice weather, the comedian just put you over the top. That's probably what it was. We had a wild weekend at my house also. We went to bed at 9. It was crazy. We watched Play with a Chance of Meatballs 2. Yeah, pretty much. Pretty much a wild life. My daughter did get a guitar. That was exciting, so she's been serenading me all weekend. 2.5. So she puts the guitar on her lap and sings Itsy Bitsy Spider. So she'll go like, strum, itsy bitsy, strum, spider, and then she sleeps a bit. There's not a lot of space in the bed, so it's like her, a half-size guitar, all of her stuffed animals, her Dora books, and then she has one of those, like one of those magnetic drawing things where like you put the pen to it and like it pops some sort of metal shavings up to the surface. So she has all of that in her bed all at once. And I can hear her when she's starting to fall asleep because she'll play the guitar, like just strum it, and then a few minutes will pass and then she'll strum a little bit more. And finally when she falls asleep, I take it all out of the bed because I'm afraid she's going to suffocate or die or something awful. You don't know. You have all kinds of crazy thoughts at night. Alright, so state of equilibrium. So we have to figure out what the rate of equilibrium is. Alright, so at equilibrium we can say that the rate forward is equal to the rate reversed. So as much product is being made as product is going back to reactant. Those rates are going to be equal. Which would be the equivalent to saying that the rate constants are going to be approximately equal. So then the concentrations have to be equal. You're getting to the point that you're not making any more of one than the other. Right, so they've gotten to a point that you're not making any more products, so you're not making any more reactants. They've kind of evened out. So then we're to the point that we're at dynamic equilibrium. Dynamic means, right, in motion. Alright, so equilibrium does not mean that the reaction has stopped. It just means there's no net gain in reactants or products. Right, when you imagine a reaction starting, you make a lot of products really, really quickly. Then after a while, you start to run out of reactant, so the reaction slows down. When we get to what we call the end, it's not the end of the reaction in that nothing else is happening. It just means as much product is going to be made has been made. And so some of the product will eventually go back to reactant, will come back to product, and so it's a little more dynamic in that way. So, let's talk about, this sounds yoga-y. It's not, positions of equilibrium. No, I guess no net change. So it means at that point there is no more change in the concentration. Alright, so let's look at some examples of reactions and we'll predict what's happening with them. Alright, so let's say I have sodium chloride aqueous. What two ions does sodium chloride break up into? Sodium with what charge? +1, and chlorine with, okay. Alright, what do we know about ions dissolving in solution? Very likely, very unlikely. Very likely, right? So, at equilibrium, am I more likely to have products or reactants? Right, we just said it's very likely for sodium chloride to break into ions. So at equilibrium, I should have more products. Right, the sodium and chloride concentrations are going to be equal to each other, but there should be much, much more of them than the sodium chloride by itself. So if that statement is true, which way should the arrow mostly be pointing? To products or to reactants? To products. So it's more appropriate to write this reaction. Right. There is a at equilibrium, some will come back, but a very small chance, a small arrow. All right, let's look at silver chloride. Based on your either remembering solubility rules, which you will need to know again. We're coming up to where you have to know all your solubility rules again. Not that you've forgotten them, but perchance you need a refresher. You can throw that into the thing to do this week. Solubility rules, and knowing that I always do 3 examples, and one's always one case, one's always the other case, and one's in the middle. If this one was the soluble one, what should sodium chloride be? Insoluble. Excellent. Sodium chloride is insoluble. So at equilibrium, should there be more reactants or more products if sodium chloride does not dissolve in water? More reactants, right? Alright, so then which way should my arrow be mostly pointing? Back towards reactants, yeah? Alright, so that's just based on stuff you know. Talking about equilibrium. This, try and get you thinking like equilibrium is really going back and forth, but there's a predominant direction it's going to want to go, so you end up with more of one thing than the other. Alright, so third scenario. Hydrogen gas and deuterium gas make a hydrogen-deuterium combo. Do you know anything about deuterium gas? Anything about hydrogen gas and how it reacts? Not really. But based on your scientific intuition, which direction, where should the equilibrium lie? If I already did one way, one's the other way. Straight in the middle. Excellent. It's going to be somewhere in the middle, where everybody's equal. So the question is, how can we predict equilibrium, the direction of equilibrium, when we don't know off the top of our head how the system's going to react? Right? In the first two, you knew stuff about solubility, so you make a good prediction. But I've been watching too much Dora. In my head, I'm like, who do we ask? We don't know which way to go. The map. Kind of. We kind of ask the map. Not a lot of Dora fans out there. Okay. Then the map pops out and sings the map song. The map song consists of I'm the map, I'm the map, I'm the map. Alright, so we're ready to talk about the equilibrium constant. Let's see, hold on. Okay. Alright, equilibrium constant has this one big rule along with it. That will make sense the more we come. I just want to put it out there so we think about it now. And then we'll look at why this is. Alright, so for all the reactions we've done so far, right, so this one, alright, that, or the one we just looked at. Right, so in these cases, I was reacting an aqueous thing to make ions, or two gases to make a new gas. We do not include concentrations of pure liquids and pure solids. So if I looked at this, I'm really saying right, when I say aqueous, I mean dissolved in water. I don't usually include the water on both sides because the amount of water is so much greater than the amount of sodium chloride I'm putting in there. The water seemingly doesn't change concentration. Does that make sense? Like if you're making your Kool-Aid mix, you put a liter of water in there and like a packet of Kool-Aid. It doesn't work the other way, right? You don't have a liter of Kool-Aid mix and you put in like 8 drops of water. That may be delicious, but you shouldn't do that. Unless you have like one of those, what is that? Like there's a packet of just sugar with like the little sugar stick. Yes, in that case, yes, that's what you're doing. But that's not what we're talking about. Fun dip is delicious. Alright, so what we're saying is that the concentration of water doesn't change. There's so much water compared to how much sodium chloride that we don't include it when we do these equilibrium statements. Alright, so let's take a look at some elementary steps and see how that comes together. Let's say I have Alright, so let's say this is the elementary step I'm looking at. And just to be thorough, we'll say it's the slow. Alright, so that's not the confusing part. If I want to write the rate of the forward reaction, I'd be looking at the two reactants, right? Forward has reactants going to products. So what exponent should my iron have? 1, good. What about the carbon monoxide? 2, right? Alright, well now I'm in equilibrium, which means I can also write a rate statement without the reverse reaction. What exponent should my iron dicarbon monoxide have? Alright, what did I say is true about the rates of a forward and reverse reaction at equilibrium? They're equal, which means now these two things are equal to each other. At equilibrium, those two rates are equal, which means now these two statements are equal to each other. We'll go ahead and write that. Alright, so now, like any good chemist, you want to get the like variables together. Alright, so we're going to get all the things that are K on one side, all the things that are in brackets on the other side. I'm going to do it this way. Alright, so now I have a statement that deals with concentrations of products over reactants, each raised their stoichiometric coefficient. equal to this rate ratio, right? How fast forward compared to how fast backwards. My big K's look like my little K's. So these are uppercase K's now. We have now found the equilibrium constant. For a given temperature. So the equilibrium constant for a reaction is a constant as long as you are looking at a known temperature, which is just a ratio of forward to backward, right? So if you're going more forward compared to more backward, that tells you one thing. Thought-provoking question. If the two K's are equal to each other, what should big K equal? 1, right? So if I'm legitimately dead set in the middle, the fraction should equal 1. If I have a bigger number on top than on bottom, should K be greater than or less than 1? Okay, what about the reverse? What if I have a big denominator? Excellent. So knowing your value of K relative to 1, you know where you are on the equilibrium scale. Alright, let's do a few more practice things, then we'll talk some more. Let me do this. Let's say I have Alright, so on my forward and reverse reaction, I have 3 oxygens making 2 ozones. If I set it up like I had on the previous stage, what goes on the top of the fraction? The ozones. To what power? Yeah. Because we consider these all elementary steps. So on the bottom should be oxygen, and which exponents it get? 3. So officially the rule is you're always going to have product divided by reactant, each raised to their stoichiometric coefficient, right? So this was a 2 raised to a 2. This is a 3 raised to a 3. So in words, that's what we're doing. Let's do one more. Ooh, this is my trick one. Good. Alright, so I have silver sulfate as a solid in equilibrium with 2 silver ions and 1 sulfate ion. Alright, so I have my forward over reverse, which is equal to my big K. What should go on the numerator? The products or the reactants? Products go in the reactant, okay? So I'll put these guys down. Does the silver need an exponent? Yes. Needs a 2. What about the sulfate? Does it need an exponent? No, there's just 1. Alright, what about my denominator? Right, so this is why it's a tricky one. it's solid. So what I'm going to say is I'll write it down and I'll get rid of it. So because it's a solid, the concentration is a constant. And we just assume it's 1. Because really, concentration is really change in concentration over change in time. And if there is no change in concentration over time, it just doesn't factor in at all. So in this case, this reaction only depends on that. Alright, so let's take a look at what does K mean in the great scheme of K's, big K. So, just like we said like 5 minutes ago, large values of K means it's going towards product. Small values of K means it's going towards reactant. So, let's take a look at just as a reminder, right, or the reverse. If I have, I guess we can do the one I had before. I say that this big K has a value of .5 times 10 to the 12th. Gigantic K. Which is bigger, the numerator or the denominator? Right, the numerator has to be bigger to have a gigantic number, right? Bigger than 1. A little bit bigger than 1, like factor of 12 bigger than 1. Really, really big. Alright, so we're at the point where there's lots and lots and lots of oxygen compared to ozone. So we say that the equilibrium is product favored. At this point, it is making a lot of product. It's very likely for ozone to fall apart to make oxygen. Alright, so then let's do the opposite case. Alright, let's talk about chlorine gas falling apart into elemental chlorine. How likely is that to happen? Not likely at all. Almost never. So the K for this what exponent should the numerator have? 2. So you can either write them out twice. You just see that. That's fine. What about my denominator? 1. Yep. Alright, if I tell you that that is .48 times 10 to the negative 38. What does that tell you about the direction that this is going to go? It's very much reactant favored. It makes almost no products. Right? Reactant favored. Alright, what is the, you probably haven't even noticed, there's been no unit on my big K's. Why is there no unit to the big K? Based on its origin, they cancel out, right? Because the units of little k forward is equal to the units of little k reverse. So lucky for you, there's no unit for a big K. Yay, which means you can't forget them. There just aren't any. No units. Alright. The last two things for today. I don't know where it went. Okay, there should be a 0.3 and a 0.4. Who knows where they went? Alright, so we had k much greater than 1, k much less than 1. Yeah, apparently they're not in there. Sorry. Yeah. Yeah. It's like based off of this point. What does it mean if my big K equals 1? Right, it means those are all equal to each other. K equals 1, which means my forward is equal to my reverse. Right, it means we have comparable amounts. They're pretty close to being equal. Everything's all canceling out. Oh, don't worry. We'll have to solve for it using quadratic equations. The quadratic equation, right? Negative b plus or minus. This is where having a fancier calculator is a good and bad thing, because you can't use them on the final. So you'll have to get used to using a regular calculator and plugging it all in. Minus b plus or minus square root of 2a squared. Yeah, good times. So we'll have to solve for those concentrations using the quadratic equation, right? With all those squares and whatnot, we'll sort it out. And the last point. What if we're not at equilibrium? That's what we're going to pick up with on Wednesday. Alright, so I have your exams. If you would like it, hang out for a few minutes. The easiest way for me to